In this video, we'll talk about what happens when you have a repeated factor in the denominator when doing the method of partial fractions. So our second issue to deal with in terms of rational functions that we cannot handle using partial fractions up to this point is when the denominator has a repeated factor in it. Right? We handled quadratics last time, now we handle repeated factors. So let's say, for instance, you wanted to do partial fractions for the following setup. How would you want to set this up? Well, your first thought might be, well, I have an x minus 1 in the bottom, and I have an x plus 2 in the bottom, so that should do it. But the issue here is, I don't get the right denominator. If I went to go to a common denominator here, I would get just x minus 1 times x plus 2, not x minus 1 squared times x plus 2. So that square has to come into play somewhere. Your second thought might be, well, let's just do this. That has the right denominator when you do common denominators. But now what's the issue? Now, this term is a quadratic. So to set this up properly, we need to think back to our quadratics from the last video and realize that's going to need two coefficients on top, an x term and a constant term. So one way you could actually set this up is the following: ax plus c over x minus 1 squared plus a b over x plus 2. That would work and that would be just fine. However, that's not the easiest way to work this out. It turns out a setup like this is also equivalent to an a over an x minus 1 plus a c over an x minus 1 squared plus b over x plus 2. These are not the same a and c, so I'll put lines over them. But I can also do the setup this way. And the reason why I like this one better is because this one's easy to integrate. I know how to integrate x minus 1. I know how to integrate x minus 1 squared in the bottom. That's also fine. What I don't know how to do is x over x minus 1 squared. That's going to require substitution and moving things around. It's going to be kind of annoying. So the easier way to set it up is like this here. And so what you want to then think about is a factor of x minus a to the k in the denominator adds a1 over x minus a plus a2 over x minus a squared plus up to ak over x minus a to the k to the decomposition. So again, from a factor of order k, right, something to the kth power, I get k coefficients, which is the theme you should see going on. If it's a linear factor, I get one coefficient. If it's quadratic, I get two. If I have x minus 1 cubed, I'm going to get three coefficients from that. And the point of setting up this way is this is easy to integrate. Let's see how this works in the context of an example. So I want to integrate 2x over x plus 1 squared times x minus 3 dx. We want to start by doing partial fractions again. This is going to need our setup from we just talked about with a double factor in the denominator. So this is going to be written as x plus 1 squared times x minus 3 is going to be an a over x plus 1 plus a b over x plus 1 squared plus a c over x minus 3. Now we can play our same tricks as before to go towards value substitution, clear denominators, and I will get the following. 2x needs to equal a times x plus 1 times x minus 3 plus b times x minus 3 plus c times x plus 1 squared. You have to be careful with this one when how you clear the denominators, because remember, the first term is just 1 over x plus 1, but I'm multiplying through by an x plus 1 squared, so I'll get two copies of that, only one will cancel, and I'll still be left with this x plus 1 here when I simplify the expression out. Now, to go for value substitution, we can first plug in minus 1 to get rid of the x plus 1 terms. So on the left, I get minus 2. On the right, I get 0 plus b times minus 4 plus 0, which tells me that b must be 1/2. I can then plug in 3. On the left side, I get 6. This is also a 0. The b is 0. And I get c times 4 squared, so that's 16. So c is 6 over 16, or 3/8. And now I don't have a nice number to plug in for a again, because I don't have any number that makes other terms go away. So I'll just have to plug in and solve out and see what I get. Let's plug in 0, because 0 is always usually pretty nice to plug in here. The left side gives me 0. On the right, I get a times 1 times a minus 3, plus a b times a minus 3, plus a c. I can clear the a term over, and then I can plug in b and c. So 3a should equal negative 3/2 for the minus 3b plus 3/8. I can divide everything by 3, so then a is negative 1/2 plus 1/8, which is 3/8. with a negative sign. So then I have my partial fraction expansion, which gives me that 2x over x plus 1 squared x minus 3 is equal to negative 3/8 over x plus 1 plus 1/2 over x plus 1 squared, and then plus 3/8 over x minus 3. This then means the integral can be written as negative 3/8 the integral of 1 over x plus 1 plus 1/2 the integral of 1 over x plus 1 squared, and then 3/8 the integral of 1 over x minus 3. And I can integrate all these out. So I get negative 3/8 log of x plus 1 plus a negative 1/2 1 over x plus 1, and then plus a 3/8 log of x minus 3 plus c. That's what you get in that case there. And that's the basic idea. When I'm doing repeated factors, I just have to have one term for each ascending power of that factor until I get to the number that are in my denominator. And once I get that, I can write that out, that expansion, and that will give me the right number of coefficients and the right generality to then be able to solve for the coefficients for the partial fractions. And those all give rise to pretty easy integrals to solve to then compute the antiderivatives of these rational functions.